Good afternoon, everyone. My name is Joshua Watson. This is a joint work with Dr. Bryson Payne, Dr. Denise McWilliams, and Dr. Mingyuan Yan. All of us are representing the Department of Computer Science and Cybersecurity at the University of North Georgia. The title of the paper we will be discussing today is Evaluating LLM-Assisted Reverse Engineering with GhidraMCP on a Graded CTF or Capture the Flag Challenge Suite. Our thesis that we hope our work will make an argument for is that while there is currently a fairly large body of work asserting that large language models are useful for reverse engineering, what that literature has not given us is a clear account of where that usefulness stops. So our contribution is hopefully to draw the line empirically on a set of binaries whose difficulty will escalate in a controlled and documented way to show where that line falls in a place that you can hopefully predict in advance. So let's talk a little bit about why this matters. So reverse engineering is expensive. It requires a lot of expertise, a lot of time. The expense is almost entirely analyst time, and expertise takes years to build. It takes a lot of time of building up a variety of different tools in order to tackle different challenges. Modern binaries are constructed specifically to consume that expertise. So symbols are going to be stripped, control flow flattened, payloads are encrypted. Just anything that we can do to mislead either the analyst or the disassembler. There are going to be anti-debug checks punishing anyone who's trying to use a dynamic tool. And basically anything that bad actors can do to slow down the progress of an analyst. So large language models offer sort of a complementary path to traditional analysis. What they're good at is that they can summarize decompiled code into sort of plain language statements. They can propose meaningful names for functions and variables that maybe are stripped of a binary. They can recognize cryptographic idioms or XOR loops or even RC4 encryptions. But the open question is not whether that model can read the code. It obviously can. The question is where it breaks, how it breaks, and at what point does it stop being useful to the analyst. And so that's kind of what we're trying to figure out here. So our paper makes three key contributions. First, a fixed four-stepped prompt playbook of analysis, decryption, an Indianness check, and a cleanup / patching plan. We are going to report the prompts we used specifically, what we found, if anything surprised us, and how the order of the steps are important in their phrasing. So we'll also talk about sort of where the model fails, and those errors tend to fall into two separate but narrow classes, one of which is hallucinations, and the other would be just simply not having the technical ability to follow through on said prompt, such as direct patching. So here's the setup. We used Ghidra 10.32. This is a disassembler, decompiler, even a patching program. It is put out by the NSA. It is open source. GhidraMCP acts as the bridge to allow us to connect Ghidra to Claude using an MCP server. So it implements the model context protocol, which is an open standard for streaming structured context to a model and receiving structured replies. in practice, it will stream functions, strings, decompiled fragments out of the model, and writes and the replies, summaries, proposed renamings, cryptographic hypotheses, patch point suggestions, back where the analyst can see it and then inspect and continue. And the model, once again, is Claude Sonnet 4. And then there is the fourth box, which I swear is not just there for decoration. The analyst is the verification loop. Everything entered into the program database has to be confirmed by a skilled analyst. So every flag was verified by executing the target binary. Every decryption proof of concept was validated by running it. And every prompt, every response, and every operation action was logged. So, yes. And then our methodology. So, our methodology fits into our environment where we used our GhidraMCP plugin. We checked it both in a Windows 11 virtual machine and a Kali Linux for convenience with scripting and patching utilities. Our tool chains were identical across both, and the platform change did not alter the protocol or the results. And each level was solved in a fresh model session with no context should have been carried over from the previous one. Our test protocol was to auto-analyze in Ghidra to build the program's database. Then we would run through our prompt sequence. And if decryption became impossible, we would request patch points and then attempt the patch points until we could get a valid executable or flag. So, and then our measurements were so time to insight or time to solve in minutes, correctness of the generated summaries, and scripts validated by running them. So did the flag actually unlock the executable? Whether the suggestions actually led to a working patch, and the frequency of hallucinations along with how we corrected them. So, and then I want to draw particular attention to the bias controls at the bottom. So this is the first thing that a careful reader would ask about, and so recent Ghidra versions handle simple string comparison and stack string reconstruction automatically. The original Escalate challenges you can probably find public walkthroughs for, so we did modify the executables with new passwords and additional obfuscation. And these variants are not currently available publicly, so the model should not have been able to look them up, and it should have been forced into genuine static analysis. And the team member who altered the binaries is not the same as the analyst who decrypted them. So the decryptor would not have had previous knowledge of the solution and would have actually had to go through the entire process manually. Let's talk a little bit about the Escalate suite that we used, which is provided by Point 3 Security, a now defunct organization, but we thankfully still have access to the executables. There are 11 levels of the reverse engineering series, spanning from Windows to Linux. I'm not necessarily going to cover all 11 here, but if you want, you can take a look at the slide and it will explain the different levels of encoding. So at the top, in green, these are static data, so they're hard-coded strings that we can find within the stack or assemble byte by byte. In the middle, in the blue, is our static crypto. So these are going to be either a single byte XOR or an RC4 encryption, including even an anti-debug checker, which thankfully we are able to get around because this is still static and not dynamic. Then in the orange, we have our runtime state. So these are going to be looking for debuggers, and they're going to have timing checks. And then at the bottom in red is going to be where the obfuscation becomes structural. So library calls will be inlined, array, decryption, and mapping as executable code, and then an anti-disassembly layer through invalid and overlapping bytes with opaque and indirect control flow. So then, once again, our 4-step prompt playbook. Our first step is simply analyze this file. So can you find the intent of the file, the validation logic, the encryptions, where the main system is, and then we validate the path through. For levels 1 and 2, this was actually enough to simply find the flag. Then our second step, once step 1 no longer returns an answer, is can you decrypt the flag? So this should elicit an algorithm hypothesis together with a runnable code. When it is static, this was able to produce correct scripts for both XOR and RC4 encryption, and this was able to get us all the way through levels 3 and 6, although there was a instance starting at level 4 where we occasionally had to call for an Indianness check. So can we check the Indianness of the key? And while this may look trivial, it is important to make sure that the RC4 encryption is correctly done and that we actually get a decisive solve. And once the model knew to check for Indianness, it was constantly able to solve all the way up through 6. And then step 4, we just ask it to clean up any code, find main, find the check password, suggest patch points if it was unable to statically decrypt, and it will rename and point out different control flow explanations through comments, and hopefully locate any anti-debugging sites. And any offsets that can be no-opt or redirected. This becomes relevant starting with level 8 and 11, and we did skip level 7 because level 8 and level 7 share effectively the same level of encryption. So we just went ahead and went to level 8. So if it fails at step 4, this is where we have to move into dynamic analysis and manual reverse engineering or direct patching. Unfortunately, at the time, either GhidraMCP, the plugin itself, does not have patching capabilities, or Ghidra may not be allowing plugins to do direct patching. And then there's also the possibility as well that Claude may have some sort of protection layer that doesn't want it directly patching or running code that it identifies as potentially malicious. So now let's talk about our outcome. So level 1 is just plain string text. Solved it with no additional nudging required. It just immediately found the correct string compare path. Level 2 is a stack assembled string. Once again, solved it no problem, didn't require any additional nudging, and recognized the bytewise construction. Level 3 is a 1-byte XOR, solved after prompting. We did have to tell it that it was a bytewise XOR. It initially made a mistake and fabricated a flag, but once it knew what it was, the decryption type, it was able to correctly produce a key. RC4 starts at level 4. This is an 8-byte encryption key. So it did solve it after a prompt. It initially was unable to correctly produce the flag. It needed to do an Indianness check. It had the key order temporarily reversed, but once we identified the correct Indianness, it was able to solve it. Level 5 is an RC4 encryption plus a flag encryption. It managed to solve it, reuse the same pattern. We didn't need to do any additional nudging. RC4 also includes a light anti-debug checker. This would potentially create a problem in dynamic solving, something in like Ollie debug or IDA. But because this was still static, it managed to solve it, and we had no issues. Once again, the anti-debug is effectively inert in a static analysis pass-through. Then we went to number 8, so we did runtime key and timing checks. We were eventually able to solve it via patching with a buffer redirect and no-opping the mem copy, but static decryption is still impossible. And once again, you would need to have a level of knowledge of how to patch a executable like this in something like Cutter. It was not able to directly identify all of the variables needed to patch out. Once again, so 7 is very similar to 6, and so we did not run it. 9 and 10 are solvable with basically the same solution as 8. And so then we did try 11, which has anti-disassembly, and it also adds inlining and various other obfuscation techniques. This is where the model really starts to fizzle out and was unable to come up with any direct solutions, so this required previous experience and know-how. Next, we have a look at our time to insight or time to solve. So with this, the human baseline is solving with 0 assistance, and then the LLM assisted, this is with our prompting alone. The way that we start the timing is from the point that we open Ghidra and allow it to do its analysis to running the prompt and finding the solution. And they are also rounded. So in this case, if it took us 4 minutes and 35 seconds, we just said it took us 5 minutes. Or if it took a little less than 2 minutes, like 1 minute and 30, we just said 2 minutes. Just to give a sort of a general comparison. So with level 1, it took our analyst about 5 minutes. That took a little under 2 minutes for the LLM-Assisted. Level 2 takes a little bit of extra time to manually, because it is sort of a bitwise encryption, so you have to put the stack together, whereas the LLM was obviously much faster in this regard. Level 3, the time takes a slight jump forward, about 15 minutes for the analyst using CyberChef, and about 5 minutes for the LLM, and this is including the reprompting necessary. So if it produced a false result, we would do an analysis, and then if the key did not open the executable, we would proceed to attempt to discover what the issue was. So that's where additional prompting was necessary. Same thing with L4. It took a little bit longer for the LM. It was about the same amount of time for the analyst, but it took a couple extra minutes for the LLM because we had to solve the Indianness problem. L5 and L6 are both a little bit more complicated to do manually. And so you see a general increase in timing. However, because the program had already learned how to do the RC4 encryption and understood the Indianness, the timing actually went down and it remained fairly static across both of these. L8, which was the first one that did require some patching. So looking at the disassembly and cutter, took the analysis, and also no-opping everything, ended up taking about 40 minutes. Thankfully, the LLM is able to correctly identify where you need to start your patching, which seriously cuts down on the amount of time the analyst needs to be looking through the disassembly in the stack. So that helps a lot here. And then sort of the same thing with L11. Now, L11, level 11, we did not actually get a full solve, but we did manage to locate a general area that needed patching. And that was the timeline here. So about half the time of analyst alone. And then let's talk a little bit about our failures. So 3 out of our 8 attempts produced an incorrect first pass output. So this is an error rate of about 37.5%. Each time it only took one corrective prompt to fix it. Where these happened, we had 2 occurrences on level 3 and 4. This was Indianness or byte order, or misreading multiple key bytes. So once our suggestive actions were done, it was able to solve it. And then we have our level 8, our first occurrence, which was it initially inferred that a decrypted binary did not exist, or a decryption operation did not exist in the binary, but once we reframed it into decoding or patching, it started being able to find some solutions. Let's see. So, yes. So, at level 3, the model read the decompiled loop and correctly inferred a single byte XOR. It produced a flag that was unfortunately fabricated in the correct format, plausible looking, but simply was incorrect. This is the first and clearest example of a hallucination in our data. And it is instructive because the model's reasoning was correct. What failed was the arithmetic it performed never actually occurred. So we instructed it to XOR each byte and show the intermediate values. And once forced to show its work, the output was correct, and we were able to confirm. At level 4, it did identify an RC4 state initialization, and which is impressive. However, it interpreted the 8-byte key in the wrong byte order, and the initial flag was worthless. So once asked to check the Indianness of the key and show its steps, with the key order reversed, it successfully produced a key, and then level 5 and 6 were able to just reuse the same information. And then basically what we learned is that the algorithm identification, while reliable, byte level representation was not, and that is why further prompting became necessary. So then, let's see. So let's talk about the difference between static and dynamic analysis. So static is something that we can find the flag, put the flag together merely by searching through the code, whereas dynamic requires us to actually run the program in order to come to a solution. So this is where the model begins to struggle when it can no longer statically analyze our executables. So what defeated it initially was our timing checks. Basically, the program has a clock running through it, and if it does not reach the correct line of code or execution within a set time limit, which is incredibly fast, like much faster than human reaction speed, obviously, the program will simply shut down. And there's just not a plain text solution that exists in the binary at this point. Everything is being built dynamically as the program is running. So static analysis would just never be able to recover that information. Instead, at this point, we can no longer ask for the flag, but we can ask for assistance with patching the executable. The goal here is to basically look at the assembly code of the executable, and by finding the correct insertion point, no-opping some code that at that point would be either harmful to the run or effectively just useless, and then replacing it with our own code in order to make it actually give us the flag. So we make it so that the program will decrypt its own already encrypted flag and then print it out for the user, and then we're able to confirm by running the executable with the flag. So let's see, let's talk about some of the structural obfuscation that occurred. So some of the defenses that the malware puts up is invalid or overlapping instruction bytes that mislead the disassembler, opaque predicates and indirect control transfers, or misleading control flow fragments. And then the decompiler output degrades, and that model then inherits that degradation directly, meaning that the level of obfuscation here is so great that the decompiler produces almost sort of like unreadable code that and it has a lot of false information, false flags that exist in order to misdirect an analyst. So how did the LLM help in this instance? We used it to narrow the analysis reason, which saves a lot of time. Certain guard branches were highlighted, and various bypass points were suggested. At this point, human hands are still necessary; they are still required, and we have to validate any of the information being given to us by the LLM so that we don't come across any unintended side effects, meaning that our patch would maybe just not run or not give us a correct solution. So because this would require a lot further, broader manual patching, we record this as a partial success, but not, or as a partial result, not a success, meaning that the solve was incomplete. So capabilities and limitations. What can it reliably do, and where is it failing? Reliably, first passed function and variable naming, um, which it inserts inline for verification. Concise intent statements from decompiled pseudocodes, which it listed as comments. Recognition of reverse engineering motifs, so decryption stubs, single byte XOR, RC4 loops, various checks, runnable decryption proofs, cross-reference and call graph summarization for navigation, patch point localization when decryption is out of reach, and logging this sessions and prompts for reproducibility at a later date. Standing limitations are hallucinations that are fluent, plausible, and wrong. So verification is not optional at this time. No runtime state, meaning that runtime derived secrets are out of reach. Decompiler dependency, so any heavy obfuscation degrades guidance accuracy. Context limits force chunking on large binaries, meaning that the LLM may have just run into issues where the amount of code that it was looking at was too big and we had to narrow its focus. Reproducibility varies across runs and model versions. So cloud inference transits, binary excerpts to a third party, and then the plugin API and Ghidra version. Any mismatches will break the integration and cause an issue. So what about the ethics of this? So lowering the cognitive cost of RE lowers it for both defenders and attackers, which is something we need to talk about. So initial risk might be asymmetrical uplift. So while generative assistance will lower the bar for, or can lower the bar for adversaries, on routine tasks, our reading is that the net effect of the offense-defense balance is plausibly favorable to defenders because of the hallucination and brittleness we documented on novel obfuscation. But this is a hypothesis that warrants longer study rather than a assertion. Exploit synthesis, which we did not exercise, but every patch suggestion in this study was strictly defensive. Production deployments should add prompt level guardrails that decline offensive synthesis requests and log the attempts. Meaning just that, if any bad actor does attempt to exploit the model itself, or is even trying to reverse engineer a, let's say not a piece of malware, but a different piece of software to either create a like a back end, or to simply gain access to paid software. Theoretically, the model should have a way to determine this and just not give an answer. Sample confidentiality, so not sharing our binary experts to a third party, and creating a possibility where this malware could be found out in the open. And then audit and disclosure. So any untraceable prompts will impede reproducibility and invite misuse claims. So we did log all our exchanges, and the corrected prompts are disclosed here for technique, but not for offensive use. Future work. So basically, where would we like to go from here if we were to continue this study in the future? we would try to integrate dynamic analysis. Um, so because the model cannot reason with runtime derived obfuscation, um, if we were to create sort of a dynamic trace collector, uh, it could capture system calls, library calls, and memory writes during a short execution. Um, Then there's top K API sequences, so written buffer offsets and contents, timing check, outcomes. So the summary is injected into the prompt alongside the existing static context, framed explicitly as observed evidence rather than as ground truth, and then the four-step playbook is simply reissued against the augmented context. Uh, This hybrid loop could potentially resolve the level 8 and level 11 failure modes in particular because it supplies exactly the runtime values and concrete control flow edges that static analysis cannot provide. And then beyond that, broader coverage into ARM64 or Android binaries, grounding the model in GhidraMCP code or data flow slices rather than pseudocode text, um, creating a graded benchmark with fixed prompts and standardized reporting of hallucination rates and recovery cost. Um, so, in conclusion, um, we treat LLM augmented decompilation as a human in the loop accelerator, but not an autonomous solver or a replacement for analyst verification. Um, we offer a four-step playbook that holds: analyze, decrypt, Indianness check, cleanup, and patch. Um, that should hopefully be able to advance the model from basic triage to verified solving at low and moderate difficulty, and then from solver to patch localization aid at higher difficulties. Um, Representation slips and overconfident summaries. So 3 out of the 8 reported levels required exactly 1 corrective prompt each, and none required model replacement, which was good. And then a boundary where things need to advance, meaning that at this point, runtime analysis is uh, not achievable, and that we are limited by static analysis. So, and then any questions can be um, directed here. You can send an email to me at joshua.watson@ung.edu. And I would be happy to speak further with you about this paper and our work. Thank you.